In our next set of reactions, we're going to look at the idea of protecting groups. And protecting groups are going to be a way for us to mask one functional group during a reaction where multiple functional groups can react. Look at the following reactions. Each of the following reactions is potentially problematic in a synthetic scheme. Pause the video and think about each of these reactions and the problems that you might encounter. In the case of the first one here, we have a Grignard reagent, which is a strong base and a strong nucleophile. It's going to undergo a reaction in a molecule that has a ketone and an alcohol. And what we know is that Grignard reagents will react with ketones, and so that's the reaction you're probably thinking about. But the fact that this alcohol is acidic poses a problem, because this Grignard reagent, being a strong base, will simply react, grab that proton, and the products that we isolate out of this reaction will be our original starting material plus a molecule of methane, which comes from that Grignard reagent grabbing that proton and essentially ruining all the reactivity that our Grignard reagent will have. In the next one, these are conditions that will make a Grignard reaction with the magnesium and this bromide, but this is also a compound that can react with Grignard reagents. So if we form that Grignard reagent, this could potentially react with itself or another molecule of our reagent. In this case here, lithium aluminum hydride is a strong reducing agent. My aldehyde is more reactive than the ketone, but what would happen if I wanted to reduce the ketone over the aldehyde? Both are reactive under the conditions of this reaction, and the aldehyde is more reactive. So when we look at the idea of protecting groups, what we're going to be doing is we're going to be masking one functional group in a reaction where more than one functional group is capable of reacting. It's going to give us selectivity. It's going to allow the group that we want to react to undergo the reaction, and it's going to hide the other group. But one of the requirements of a protecting group is that you have to be able to put the protecting group on your molecule, and you have to be able to get your protecting group back off of your molecule in order to reveal that functional group that you hid. So in the first part of our discussion on protecting groups, we're going to be talking about the protection of ketones and aldehydes. And when we protect ketones and aldehydes, we're going to protect them as acetals, ketals, thioacetals, or thioketals. What we know about acetals, ketals, thioacetals, and thioketals is that they will go on under acidic conditions and they will hydrolyze under acidic conditions. That means that when we use these reactions, we have to avoid reactions that have acidic conditions so that our acetals, ketals, thioacetals, and thioketals are going to be stable to basic conditions using reagents like Grignards or our reducing agents, but they will hydrolyze under acidic conditions. We could use any acetal, ketal, thioacetal, or thioketal as a protecting group, but often we use our diols or our dithiols as reagents for this type of reaction. But again, any acetal, ketal, thioacetal, or thioketal could be used as a protecting group. So they're going to be stable under basic conditions, and they will hydrolyze under acidic conditions. So it's important to understand the limitations of your protecting group. So if we look here at a reaction sequence, we saw this reaction sequence in our opening discussion. And we said that this compound contains both a bromide, which we want to react under the conditions of a Grignard reaction, and a ketone, which we don't want to react initially under the conditions of a Grignard reaction. So what we're going to do is we're going to protect this ketone, which means we're going to hide that ketone. We're going to make it look as though our molecule does not have a ketone so that we can get good reactivity here for the bromide and the other series of steps that we want to accomplish. So the way that we're going to protect this ketone is as a ketal. So I'm going to take this ketone and I'm going to treat it with any set of conditions that will allow me to form a ketal. In this case, I'm going to use ethylene glycol as my reagent. So that gives me this ketal. This is my protected ketone. And that ketone is protected as that ketal. So that under the conditions of this reaction, this carbon right here is this carbon right there. When I started this reaction, it looks like a ketone, and in the second step, I've made it look like a ketal. This ketal is stable under basic conditions for other reactions. This ketone is not. So in my next step, now I'm going to do my intended reaction, and that is the formation of a Grignard reagent and the subsequent reaction of the Grignard reagent. So I'm going to treat this compound with magnesium and followed by carbon dioxide and an acid workup. And during this series of steps, what's happening is step 1 is reacting with this bromide in order to make my Grignard reagent. Step 2 reacts the Grignard reagent with carbon dioxide in order to make a carboxylic acid. And then in step 3, this is going to be the reaction that quenches my Grignard reaction, stops my reaction from happening, and I can also use this workup step to remove that ketal protecting group as well. So that in this reaction, this workup step right here is going to accomplish 2 things for me. This workup step is going to quench my Grignard reaction. That means it's going to stop any additional Grignard reagent from reacting, but it's also going to remove my protecting group. Okay, it's also going to remove my protecting group in one step. Now, I have a second way that I could run this reaction if I wanted to keep my protecting group intact, and that's this pathway here. If I wanted to do my Grignard reaction, but then keep my protecting group intact, the steps that I'm going to use look like this. First, I'm going to treat my protected ketone compound with magnesium to make the Grignard reagent, then with carbon dioxide. Then in step 3 here, I'm going to specify that this reaction is going to take place with a dilute acid workup. The emphasis here is on the fact that this acid workup is dilute. That means it's going to have enough protons around to kill that Grignard reagent, but we're not going to have sufficiently acidic conditions in order to remove that ketal. So in this case, under the dilute acidic workup conditions, my ketal remains intact. But what I have done is I have turned that carbon with the bromide into I have taken this carbon that originally had the bromide, and I now added a carbon to that carbon chain, and I have a carboxylic acid functional group. There's a lot of reactions I could do from this point, and so I have to remember that my ketal is stable to basic conditions and will hydrolyze under acidic conditions, so I need to be very careful with the conditions of my reaction as I continue to go forward. So if I wanted to convert that carboxylic acid to an acid chloride and then to an amide, I could use thionyl followed by ethylamine in the combination with triethylamine in order to make this amide. And as I go throughout this step, notice that my ketal remains intact. Then I could take this compound and I could do a reduction with lithium aluminum hydride followed by an acid workup, and I would get this product. Notice that my acid workup conditions in this reaction did a hydrolysis of my ketal, and I have my ketone back. And also remember that when you have an amine under acidic conditions, your amine is going to be protonated. Okay, whenever you have an amine under acidic conditions, it will protonate. So that overall this synthesis protects my ketone that I have at the beginning as a ketal throughout a series of steps. And then at the end, when I'm ready to remove that ketal, I can do that in a workup step. If I have more concentrated acid, let that workup step sit a little longer than I normally would, but I can accomplish that by writing H3O plus workup rather than my dilute H3O plus workup that we specified here to keep that group intact. As another example, I have a molecule like this one. As another example, I have a molecule like this one. It contains both a ketone and an aldehyde. And if my goal is to do a Grignard reaction, I want to have selectivity on that reaction. So if I want to selectively react the ketone over the aldehyde, I can start by protecting the more reactive aldehyde as the acetal, so that when I treat this compound now with the Grignard reagent, my ketone will react with the Grignard reagent, it won't touch the aldehyde, and I can isolate a product like this one where I've selectively reacted the ketone and left the aldehyde intact. So this synthetic sequence starts with my more reactive alcohol, my more reactive aldehyde being protected. So I'm going to protect that more reactive aldehyde as the acetal by adding ethylene glycol and acid in order to give me this product here. Now this acetal, this is protected. My aldehyde is now protected, which means it won't react under the conditions of the Grignard reagent, so that when I treat this compound with methyl magnesium bromide, the methyl magnesium bromide reacts here with the ketone. And if I use my acid workup conditions, where I don't specify the dilute acid, I can quench both my Grignard reaction and remove that protecting group, giving me the final product where my ketone reacted and my aldehyde was intact. Notice that if I treated this compound with a Grignard reagent, my aldehyde would react first because it is more reactive, but I wouldn't get good selectivity because of the reactivity of the Grignard reagent. So that this H3O plus workup step is going to quench my reaction and remove my protecting group.